I've been doing this a lot recently, and this classic third grade demo actually led me to a discovery that I don't think has been reported in the scientific literature. It also made me realize that the classic explanation for how static electricity works doesn't really work. This is the moment when I understood that I actually know nothing about static electricity. In third grade, you and everyone else was taught that balloons like electrons more than hair does, so when you rub, electrons move from your hair to the balloon. But what if I rub two identical balloons against each other? There is no reason why electrons would prefer one piece of red latex to another chemically identical piece of red latex. So according to the classic explanation, what should happen here is nothing. Nothing should happen. But watch this. Not only do both balloons seem to be getting a static charge, but it also seems like both balloons are the same sign. When you cosplay a scientist on the internet, it is very easy to fool yourself into thinking you've discovered something new or done something special when in fact you haven't. I mean, I can sit here and say, look, these balloons repel. I shall call this the Zaidan effect. But I actually need to do a little more work here. I want to start by measuring the charges on each balloon scientifically. Now, you'd think that I could use something that you also learned about in high school. This thing, an electroscope. You'll notice this is the chemistry version of an electroscope because I made it with a beaker. See? But an electroscope is useless for this because it can only tell you whether something is charged, not whether that charge is positive or negative. And I obviously need to know what sign these balloons are. So instead, I'm going to buy an electrometer, which detects charge, both sign and amount. $600! I'm going to build my own electrometer. And the first thing I need to do that is a voltmeter, because that can tell us whether something is positively or negatively charged. Problem is, voltmeters only go up to about 600 volts, and static charges are much, much higher than that. Even the shock you get after walking across a carpet and touching a metal door handle is probably in the thousands of volts. Now, one of my favorite YouTube channels, Electroboom, tried to use a bunch of resistors to divide the voltage down to the point where it could be read by a voltmeter, but even he couldn't get it to work. And if Matey can't do it, I mean, can I do it? But Matey didn't have this paper, which describes a really ingenious way to measure extremely high voltage and by extension to measure static charges. And the best thing about this device is that it's cheap as hell. It uses a pencil, a $5 breadboard, and a capacitor that was maybe $1, but of course I had to buy like the 100 pack. This device allows me to tell whether something is positively charged or negatively charged, and here's how. If I bring, let's say, a negatively charged object close to this pencil, all the free electrons in the graphite will be repelled from the negatively charged object, and they will move down this wire and into this capacitor. If I bring a positively charged object, the opposite thing will happen, right? Electrons will be pulled out of the wire and into the pencil. So if the voltmeter is reading a positive voltage, that means that the object I'm holding close to the antenna is positively charged, and if it's reading a negative voltage, then the object is negatively charged. Let's try this out. This was once a rabbit, and this is PVC pipe. And if I just quickly rub these a little bit, and then first I have to ground the system and discharge the capacitor. And now I will read. Yeah, look at that. Woo! So as you can see, I'm getting minus 11 millivolts, which means that this object is negatively charged. All right, so let's do the crazy balloon experiment again. I took two balloons, inflated them, rubbed them together, and confirmed that, yeah, they do both charge up negatively. Now, I was so shocked and appalled that I had seemingly violated the law of conservation of charge that I repeated the experiment with different sized balloons. Same manufacturer, in fact, same order from before, but just a different color and a different size. And again, both balloons were negatively charged. Now, one important way to make sure that you're not fooling yourself in science is to try and confirm your results using two, or ideally more than two, completely independent methods. The fact that the balloons repel each other is one method. Not very rigorous, but okay, it's something. My homemade charge detector is another method, and I just realized that because these balloons are charging up negatively, there's another, actually much simpler method I can also use to confirm these unbelievable results. And the method starts with this, just a regular strip of plumber's tape, also known as polytetrafluoroethylene tape. If you rub this stuff with pretty much anything, it'll pick up a negative charge, thanks to all the fluorine in its chemical structure. When I bring my hand close to the strip, it's attracted to it. So you might think that my hand is positively charged, and it could be, but it could also be neutrally charged, because the strip itself is so negatively charged that it will actually induce a positive charge on the surface of neutrally charged objects. And you can see that here. I'm bringing all kinds of neutrally charged objects close to this strip, and it's attracting every single one. However, if we have an object that we suspect is negatively charged, it should repel the strip. So let's see. Oh yeah. Oh yeah. Okay, so that's negatively charged. What about this other balloon? It is! Look at that! That's unequivocal. Both are repelled. So what's going on? And that's when I realized I was doing the exact thing that I just warned you not to do from 5 minutes ago. Look back at this footage and see if you can spot my mistake. Do you see it? I got so excited to measure the charge on the balloons after rubbing them that I didn't even think to measure the charge before rubbing them. Which is important because I'm trying to isolate whether rubbing the balloons makes them negatively charged. And if they're already negatively charged before I rub them, I should know that. So let me try this again. I'll grab a couple balloons, inflate them, and check their charge to make sure it's 0. It's not 0. Huh. Both balloons are negative before I even start rubbing them. Which, just quick aside here, this makes the whole story even weirder because I'm now bringing these two objects together, each one of which already has more electrons than it should, and somehow vigorous rubbing doesn't dislodge any of these subatomic particles that repel each other and want nothing more than to get as far away from each other as possible? What? I just had a thought. What if inflating them makes them negative? So we're gonna just try this with uninflated balloons here. Wow, okay. Both of these are neutral. Weird. Let me inflate them and check again. Okay, this one's negative. And this one is too. So inflating a balloon charges it up. What? I thought that I was rubbing two neutral balloons together and that was giving them a negative charge. But actually, I was fooling myself because what I was really doing was inflating each balloon. That was giving each one a negative charge. And then I was rubbing those two negatively charged balloons together and they somehow both stayed negative. Now, that is deeply weird, but that's a whole other question. What I want to know is if I start with two neutral inflated balloons and I rub them together, what happens? Do they charge up? And if so, how? Now, the problem is, because the damn things charge up when I inflate them, I need a way to discharge them. And it's not as easy as it first seems because I can't just touch them to a ground wire because they're insulators, so they won't allow current to flow. How do I do that? I happened to be interviewing a couple of static electricity researchers that week, and they told me about this device, which is pretty genius. It generates what are called soft X-rays. These are lower energy X-rays than the ones used in a doctor's office, but they're high energy enough to knock electrons off air molecules. That creates positively charged ions, and it also creates electrons, right? Because you've just knocked an electron off. Those electrons hit other molecules, which make them negatively charged. So these soft X-rays overall generate both positive and negatively charged ions, and those ions are attracted to oppositely charged objects, and over time, they neutralize them. Unfortunately, when I checked on the price of this thing, it just says contact us, and that's how you know you'll never be able to afford it. But then I found a much cheaper way. This thing. This is basically a taser. And it's useful because sparks also generate ions, which should hopefully neutralize the balloons. Okay, so let's see if my taser can discharge a previously charged balloon. And I'll spare you all the details, but annoyingly, it couldn't. So I went back online and I found something kind of sketchy called a positive and negative ion generator. And for $20, yeah, sure, I'll give it a shot. So to test this thing, I charged up a strip of plumber's tape, and I put the ion leads right beneath it. And then I put my hand to the tape, and as we'd expect, it attracts my hand, because remember, the negatively charged tape is inducing a dipole in my hand, and so they attract. And then I turned on the ion generator, and immediately, the tape just dropped. What? Get out of town. All the charge is gone. The next thing I'm going to do is test whether my newfangled discharge station right here is able to discharge the charge on a balloon. Inflate, discharge, check the charge, make sure they're neutral. It worked! Oh, wow. Okay, now, that's amazing. It worked, and I can't, look, I'm holding my hand here, I can't feel any static charge. I don't know what to do with myself because that worked. Okay, so now that I can measure charge and discharge things, let's confirm that identical balloons can in fact charge each other up. So, inflate, discharge, check the charge, make sure they're neutral, and they are, and now I can finally rub them. And yeah, rubbing does in fact charge them up. And both of these balloons got negatively charged, though strangely, not to the same amount. Like this one read minus 1.2 millivolts, and this one read minus 0.3 millivolts. This is the moment when I understood that I actually know nothing about static electricity. I performed that last experiment on May 7th, 2025 at 11:36 a.m. And then I got kind of busy. I was working on other videos, and before I knew it, 7 days had gone by. On May 14th, at 11:59 a.m., I attempted to replicate the experiment, as any good person who pretends to do science on the internet should. Now both attract, so yeah, that's weird. And for the life of me, I couldn't do it. Are you kidding me? I tried it 3 times with 3 sets of balloons, and it just wasn't working. Positive. And when I say it wasn't working, what I mean is that the balloons were charging up, negative, but they were charging up the opposite way. One was getting negative and the other was positive. Positive again. Which, don't get me wrong, is also strange. Remember, the chemical composition of these balloons is identical. They're from the same batch, so I wouldn't expect them to charge up at all. But the fact that I redid everything the exact same way and was getting a different result was deeply, deeply dispiriting. Now I really don't know what's going on. And then I realized that not everything was the same. I live in DC, and I shot this in May, and May is the month where DC turns into a swamp. So I went back and checked the weather records. On May 7th, the day I did the experiment the first time, the outdoor humidity was 59.3%. On May 14th, the day I did my replication attempt, the outdoor humidity was 90.1%. I'd say that's different. So I cranked my dehumidifier to its lowest setting, turned on a fan, waited a few hours, and I tried the experiment again. And you're expecting me to say, and it worked. It did the exact same thing that it was doing before. But no, it did something else. I did the same experiment with 3 fresh pairs of balloons. Just keep in mind here, by the way, I'm not reusing any balloons. After every experiment, I pop them and I get new ones. Die, balloon, die. And all 3 times, I got the same very strange result. 1 balloon out of the 2 was moderately or strongly negatively charged. And the other balloon... Wait, what? That's negative, but if I go a little this way on the balloon, if I rotate the balloon, it's positive? That's wild. There's not a way to explain that. Okay. I mean, that one is... Yeah, like that one is deflecting a lot. Yeah, no matter how I rotate this balloon, there's no attraction. But this balloon, look, it's almost like part of this tape is attracted and part is repelled. All right, so I just did this twice, and the first time I got 2 negatively charged balloons, with some interesting nuances, and the second time I got 1 negatively charged balloon pretty uniformly, and another one that was like neutral, positive, a little bit of negative, with some nuances. The important thing is that what's happening now is quite different than what was happening this morning. And the difference is I've been running my dehumidifier for 3 hours, 3 solid hours. According to that thing, humidity levels have dropped from about 65% to about 50%. So that's a big change. So let's do it a third time. Look, this one is pretty uniformly negative. Like, I can turn it any which way, and most ways that I turn it, the PTFE strip is repelled. But this balloon, oh, now it's positive in the middle. What if I turn it this way? Okay. Or I don't know if it's positive, but it's at least neutral. Nope, that's negative. But then it goes to 0. Weird, what if I like rotate it? Okay, that's 0. If I rotate, minus 2, minus 3, minus 4. Okay, so the side of this balloon is strongly negative, or medium strong negative, but then if I go back to the front of it, 0. Oh, maybe even a little positive. Wow, right here on the balloon is reading as negative. Let's keep track of that spot and see if it repels the strip, and it does. It does repel the strip. Whereas if I turn the balloon this way, I think it'll attract. Yes. This is heartening. It's telling me that my experiments from a week ago were not just me screwing up. I mean, I'd consider that a partially successful replication, although yes, if I were writing this up for a journal, I would have to repeat this like 100 more times, and I would have to buy an actual electrometer, and I would have to replace the main flaw of my cheapo setup here, which is the pencil. The problem with the pencil is that it can't really detect the charge on a large object like a balloon. To do that, I would have to buy a very large metal pail, something that I could put an entire balloon into and then make it into a Faraday cup. But that's beyond the scope. Anyway, speaking of publishing this in a scientific journal, I wanted to see what actual practicing scientists, in other words, real scientists, had to say on the topic of rubbing two balloons together. And wouldn't you know it, there are not a lot of papers out there on this. Can't imagine why. Anyway, I found just two. One of them does not have a methods section, so we're going to ignore that one. The other one was published in 2008 and very rigorously investigates rubbing two balloons together, although they used different balloons than I did. Theirs looked kind of like water balloons. They were much smaller and thinner than mine. Anyway, that paper also found that the balloons charge up opposite to each other, to the point where the attractive force is actually strong enough to suspend one balloon from the other. And importantly for my purposes, the authors did not report a single instance of the charges being the same sign. Now, I also asked a bunch of AI tools to look through the scientific literature as well, and they also only found the same two papers that I did. And at this point, I allowed myself a small bit of hope, wondering if perhaps I was the first person on Earth to know that if you rub two neutral balloons, sometimes they both charge negative. Did I just discover something? And that's when I did a regular Google search, just regular Google, not Google Scholar, and found this. Once the balloons have been rubbed together, they become charged. This charge is usually negative. And look, they repel each other. And this is not a scientific paper. This is a blog post from a balloon company. My big research breakthrough, scooped by a blog post on a balloon company website. Actually, though, I will say, it did make me feel good to know that somebody else in a different state, working with different balloons, had achieved the same result that I had. I mean, in science, when two different labs come up with the same result, that's called a successful replication. So you know what? I'm going to take it. I will take it. So I went back to Google Scholar and I broadened my search beyond balloons, meaning are there any other experiments in which identical materials charge up the same way? Turns out, yes. In 2018, scientists published a paper in which they reported touching about 10 different pairs of materials together, and many of them charged up the same direction. Look at this graph. Each pair of columns represents about 30 times that two materials were brought into contact and their charges measured afterwards. Now, the y-axis is charge. Up here is positive, down here is negative. Now, you can see that when two pieces of PVC were touched to each other, polyvinyl chloride, were touched to each other, they charged in opposite directions, which is, I guess, what I'll call normal, at least normal insofar as you wouldn't expect two identical materials to charge up. At least it had been reported in the literature before for a long time. But when all of these other materials were touched to another piece of the same material, they all charged in the same direction. Most of them charged positively, including sodium chloride, though I have to say, this was not just like table salt. These were ultra-pure wafers of solid sodium chloride. But quartz and calcium fluoride charged negatively. So what is happening here? Where are the extra charges going to or coming from? To answer that question, the scientists did something incredibly clever that I wish I had thought of. They contacted two pieces of material and then immediately after pulling them apart, measured the charges, like half a second after. And then again at 1 second, 2 seconds, etc. And what they found was this. Immediately after contact, the two materials do in fact charge up in opposite directions. Charge is conserved. But then one of the materials just switches sign. For example, the negatively charged piece of mica becomes less and less negative. Then it goes neutral, and then it becomes positively charged, and then more positively charged. The authors don't propose a mechanism for what they think might be happening, but whatever is happening, I bet the same thing is happening with the balloons. Like right after rubbing, one is positive and one is negative, and then over the course of 1 or 2 seconds or even less, one of them flips sign and becomes the same sign as the other one. What exactly is going on? I don't know, and science doesn't know either. I did a bunch of research, and paper after paper said the same thing, which is we do not understand the basic mechanism of charge transfer when you touch two things together or rub two things together. That explanation you got in the 3rd grade, oh, the electrons come off your hair and get on the balloon, yeah, that might be happening, but it might not. We just don't know. Some people think it's the electrons. Others think it's free radicals. Others think it's adsorbed hydroxide ions. Others think it's charged bits of the material itself. And annoyingly, the mechanism might be totally different for rabbit fur and hair than it is for balloons. All of this is to say, none of this makes any sense yet. This is cutting-edge chemistry research, and if anyone ever tells you that they understand static electricity, you tell them that they're wrong and send them a link to this video.